So next step, we're going to cut this guy in half. So, and then we're going to start over. So we cut this in half. What do we form when we cut it in half? So 2 3-carbon sugars, but what are they? Glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. So they're both 3 carbons. What do you suppose glyceraldehyde 3-phosphate looks like? Sweet, it's an aldehyde. And what do you suppose it looks like at carbon 3? Good, it's got a phosphate. So and at carbon 2, so there's our glyceraldehyde 3-phosphate, dihydroxyacetone phosphate. Being that it's dihydroxyacetone phosphate, suppose that indicates. What kind of sugar is this going to be? Being that it's dihydroxyacetone phosphate. It's a ketose instead of an aldose. So you get 1 aldehyde sugar, 1 ketose sugar. This is your DHAP. So, and this I'm going to call G3P, as you see on your map. What's the name of this enzyme? And this one might not be so intuitive. Aldolase. So in this case, aldolase is what leads us here. And this is a little bit puzzling. So you guys remember your aldol condensations from OChem? Good times. So this actually undergoes what's called a reverse aldol. In an aldol condensation, an alpha carbon attacks a carbonyl. An alpha carbon attacks a carbonyl. And so in this case, if we had one of our alpha carbons attacking the carbonyl of the other molecule, we might actually form this bond right here. And actually going backwards would actually be an aldol condensation. What we're doing in going back is a reverse aldol. But that's why they call this thing an aldolase. I wouldn't worry about it too much, but that's why they give it the name they do. So if it helps you memorize the name, great. If not, sorry. Cool, so now we've got 2 3-carbon sugars. Where's this 3-carbon sugar ultimately going to end up at the end of glycolysis? Pyruvate, where's this one going to end up? Pyruvate, sweet. So ultimately, DHAP does what? Isomerizes and turns into glyceraldehyde 3-phosphate. Now, what do you suppose we might call something that isomerizes a 3-carbon phosphorylated sugar? An isomerase, and in this case, a triose phosphate isomerase. Every once in a while, things are actually named for a reason. So at least that's helpful. It's just an isomerization. Instead of having a ketose, I wanted it to be the corresponding aldose. So, and again, probably going to get there through a keto-enol tautomerization yet again. Cool, so now we've actually got 2 glyceraldehyde 3-phosphates. We're only going to follow one of them. Just keep in mind, everything from here on out is doubled. We've got 2 glyceraldehyde 3-phosphates. Cool, quick review. So if I have an alkane, in fact, you know what, we'll do a 2-carbon alkane. If I oxidize it one step, what do I get? I get an alcohol. If I oxidize it again, what do I get? Notice now I got 1 bond to oxygen. If I do it again, I should have 2 bonds to oxygen. get the corresponding aldehyde. If I oxidize it again, what do I get? Now I get the carboxylic acid. So, and if I oxidize it finally once more, what would I finally end up with? How do you get 4 bonds to carbon here, or 4 bonds to oxygen? So I'd get CO2. So if you keep this in mind, notice 1 bond to oxygen replaced a bond to hydrogen. Now I only have 2 hydrogens, I used to have 3. So oftentimes when we do these oxidation steps, sometimes you'll see them called dehydrogenases. Whether I gain bonds to oxygen, look at it from that perspective, or lose bonds to hydrogen, look at it from that perspective. So sometimes you'll see why we name things the way we do. So you really want to keep track of oxidation steps. This is super, 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 super important. So notice it's redox. If you do oxidation, you have to do reduction at the same time. And this is super important for part of glycolysis. So we're about to see one of our oxidation steps. So in this case, right now, we have glyceraldehyde 3-phosphate. It's an aldehyde. If I oxidize an aldehyde, what do I get? Carboxylic acid. In our case, we're actually going to look at it as a carboxylate, because at pH 7, it'll exist in the conjugate base form, but that's still an oxidation. So in this case, we now have 2 molecules of glyceraldehyde 3-phosphate. So what do we end up with after the next step? So, cool, what am I looking at? 1,3-bisphosphoglycerate. So our glyceraldehyde is no longer an aldehyde, it's a carboxylate. So we'll come back to that in a sec. So, and it's 1,3-bisphosphoglycerate, right? So this is glycerate. So if it's 1,3-bisphospho, what do you suppose is different? I'll put a phosphate on carbon 3, and we'll actually put a phosphate on the carboxylate as well. Keep in mind, this is not your normal phosphate bond right here. This is actually a phosphoanhydride. So it kind of looks like it's an ester from the carbon, and if we drew the phosphate out, it would look like an ester from that, and technically it's actually an anhydride. Whereas normally when you attach the phosphate to the alcohol, that's what we normally think of. So as being your typical phosphate ester.
So is that high energy intermediate?
So this is your first high energy intermediate. So, and what's special about high energy intermediates? Yeah, they're on the exam, that's right. So, but they can fall an awful long ways downhill, if you will. So maybe releasing a fair amount of energy in some form. Cool, what's the enzyme that took care of this one? Glyceraldehyde 3-phosphate what? Oh, dehydrogenase, look at that. So, and if you see the word dehydrogenase, you should think probably an oxidation. So, and in this case, it was. So our aldehyde became a carboxylate, oxidation. But if oxidation took place, what has to simultaneously take place? Reduction. So who are our big reduction cofactors that we'll talk about today? There's 2 of them today. So NAD plus NADH and FAD FADH2. Which one's involved here? Good. If you recall, we looked at it from the perspective of our carbon substrates, but we can kind of look at it here. We said losing bonds to oxygen, we could look at oxidation from that gaining bonds to oxygen, look at oxidation from that perspective, or losing bonds to hydrogen was oxidation. Kind of convenient here, it looks kind of, from the formula, it's more complex than this, but it looks like we're gaining hydrogens, and technically this is a reduction. So, and NADH and FADH2, those are also high energy compounds, which will cache in another day. Cool. So, but if you recognize that oxidation has taken place, then you better have some sort of cofactor getting reduced simultaneously every time. Has to happen in some way, shape, or form. Okay, so 1,3-bisphosphoglycerate now turns into what? 3-phosphoglycerate. So we still got glycerate. And it still has a phosphate group at carbon 3. Where'd the other one go? ATP. again, don't forget we're doing this twice. We have two 3-carbon sugars that are coming from glucose doing this. So we're actually getting 2 ATPs, essentially, per glucose molecule at this step. What's our enzyme? Phosphoglycerate kinase. That's kind of confusing. Usually we see the word kinase and we think, oh, ATP gets used up, but not here. So in this case, ATP actually gets produced. So, and again, sometimes your enzyme names seem to be a little backwards. This is one of those cases. So this one kinase, I don't know that we'll see this again today, this one kinase actually leads to the production of ATP as we follow it through in glycolysis this way. So again, a lot of these reactions are reversible, and we'll see that in gluconeogenesis, and maybe that's where some of the backwards names come from. So, but in this case, it's a kinase, but it's actually resulting in the production of ATP. This is obviously a really important step. We're getting our first energy production. So far, how many ATPs have we used up along the way? 2. How many have we now produced? 2. We're now energy neutral. And I say that, but technically, we've also produced a high energy NADH along the way. And maybe we get a chance to cash that in later, maybe we don't, we'll see. Cool, where do we go from glycerate 3-phosphate? So what do you suppose happens if this is glycerate 2-phosphate? Cool. Simple isomerization. And what's the name of our enzyme? Phosphoglycerate mutase. What could they also have called it that might have been a little more helpful? You might have called it isomerase. They didn't. So, but mutase kind of sounds similar. So our phosphoglycerate mutase. Cool, so now we have our 2-phosphoglycerate. Where are we headed from here? So what is it? Phosphoenol pyruvate. What's an enol? So an enol is an alkene and an alcohol from the same carbon. So if we kind of look here, we lose him, my bad. Does this thing look like an enol? I told you it was an alkene and an alcohol from the same carbon. I don't even see an alcohol on this thing. Why don't I see an alcohol? It's phosphorylated, but that right there, that's your enol. The same carbon's both an alkene and an alcohol. Cool, this is your phosphoenol pyruvate. This is also technically a what? High energy intermediate again. And pay attention to your high energy intermediates. Make a notation of which is which. Make a note on your big sheet if you want to. So, but keep in mind where your oxidations and therefore reductions take place. Keep in mind your high energy intermediates. Keep in mind where ATP is produced and used. So keep track of the overall numbers. So, and as we'll see, really keep track of regulation of everything. And I'll emphasize that so many more times throughout the night. So from phosphoenol pyruvate, where are we headed? Pyruvate. Now I got to remember what pyruvate looks like, and this is definitely one you want to know. So what just happened here to my enol? It what? Well, it did lose its phosphate group. That's cool. We're going to keep track of that in a sec, too. So, but what do enols, what are they famous for? Tautomerizing, what do they tautomerize to? They're keto form. That's what happened. This is just a keto enol tautomerization. It is not an oxidation, FYI. So if you notice, you might be like, wait a minute, Chad, that carbon got another bond to oxygen. That's true. But this carbon got another bond to what? Hydrogen. Somebody gains an oxygen, somebody gains a hydrogen, it's a wash. It's not oxidation or reduction. Where'd that phosphate go? Sweet. Cool, and again, keep in mind this is times 2. Cool, we've now finally got net energy production. So in this case, how many ATPs did we use up? 2. You should remember where that happens. So how many ATPs have we produced? 4. What's the net production then? 2. Cool, that's glycolysis. You should know where the ATP is used up, you should know where it's produced, and you should know it's a net production of 2.